Welcome back to my lectures on groups, rings, and fields. Our next topic is on factorization of polynomials over a field. Our main focus is on solving the polynomial equation. If f of x is a polynomial, find the value of x. And we changed the idea of solving this polynomial into finding 0 of a polynomial. And we did it using a evaluation homomorphism from f of x to e, where f is a subfield of e and alpha belongs to e. Then what we are seeing is that if f of x belongs to f of x, and if there exists an alpha in E such that phi of alpha of f of x is equal to 0, then alpha is the 0 of f of x. And that is exactly the value of x when you solve this equation. Now, we know that f of x is an integral domain. That means if g of x times h of x equal to 0, then either g of x equal to 0 or h of x equal to 0. Well, suppose we want to find the zeros of f of x in f of x, and if f of x can be written as g of x times h of x equal to h of x, then phi alpha of f is equal to 0 if and only if phi alpha of g times h is equal to 0. Because f of x is a integral domain. Because f of x is equal to g of x times h of x. Right? And that implies phi of alpha of g is equal to 0 or phi alpha of h is equal to 0. Which means that we can reduce the complexity of finding 0 of a polynomial by factorizing it. See, when you say f of x is equal to g of x times h of x, that means g of x and h of x are factors of f of x. and if we can write it as a polynomial of degrees less than the degree of f of x, we are reducing the complexity of finding the zeros of f of x by finding the zeros of g of x or h of x, because these polynomials are of lower degree. So the factorization has an important role in finding out the zeros of a polynomial over a field. So our next attempt is to find tools that will help us factorize a polynomial. Let us start with the division algorithm. We are familiar with this algorithm in elementary number theory using the set of integers. If you take two integers, let's say 23 and 7, we can express 23 as 7 times 3 plus 2, where 2 is strictly less than 7. And this expression is unique. And we are going to extend this idea into the ring of polynomials. And that is what the division algorithm is. So let f of x is equal to an x to the power of n plus dash dash a0, and g of x is equal to bm x to the power of m plus dash dash b0, be two polynomials in f of x such that an is different from 0, bm is different from 0, and m is strictly greater than 0. We don't want g of x to be a constant polynomial. Then there exist two unique polynomials, q of x and r of x, such that f of x is equal to g of x times q of x plus r of x, and the degree of r of x is strictly less than degree of g of x. So the proof is very simple. Let S is equal to the collection of all the polynomials of the form f of x minus g of x times s of x, where s of x belongs to f of x. So if 0 belongs to S, then f of x minus g of x times q of x equal to 0 for some q of x in f of x. And that implies f of x equal to g of x times q of x. So that means the theorem is true if 0 belongs to S. R of x is equal to 0 there. And R of x equal to 0 means the degree of R of x is strictly less than the degree of g of x, because m is greater than 0. Now let 0 does not belong to S. That implies that implies let R of x be a minimal, a polynomial of minimal degree. In S. Okay. So what does that mean? And that implies f of x minus g of x times q of x is equal to r of x for some q of x in f of x. We are almost there, but the thing is, we need to show that the degree of r of x is strictly less than the degree of g of x. So let r of x is equal to ct x to the power of t plus dash dash c0, where ct is different from 0 and t is greater than m. We are assuming that r of x is a polynomial of degree greater than the degree of g of x. Now we will consider a polynomial. Consider f of x minus g of x times q of x minus ct by bm of x to the power of t minus m. ct by bm. Bm is different from 0 because that is how we chose. ct by bm times x to the power of, and ct is also different from 0. And x to the power of t minus 1, this is going to be greater than or equal to 0 because t is greater than m. So it's strictly greater than 0. But let's assume that it is greater than or equal to m because that is what we want to prove. So this can be 0 or greater than 0 of g of x. Okay, and that is equal to f of x minus g of x. This is what? This is actually r of x minus ct by bm x to the power of t minus m g of x. And what is this? This is actually ct x to the power of t plus dash dash c0, that is r of x, plus or minus, sorry, minus ct by bm x to the power of t minus m. This is actually bm x to the power of m plus dash dash b0. So when you expand this one, you will get ct to the ct x to the power of t, and here if you multiply, this will be ct x to the power of t. So both the ct x to the power of t is cancelled off. So what is going to remain? What is going to happen here is it's going to be another polynomial r1 of x, where degree of r1 of degree of R1 of x is less than t, because we don't have a term with the x to the power of t. We have only the terms which has got a power t, less than t. So this is actually a contradiction because this actually because this belongs to S, because you can take g of x as a common factor and you have the same form as this. So R1, so this belongs to S means the degree of R1 is less than the degree of R, which is a contradiction, and that implies R1 of x has a degree less than the degree of g of x. Now we need to show the uniqueness of this. So let q1 of x and q2 of x and r1 and r2 of x be polynomials such that f of x equal to q1 of x, sorry, g of x times q1 of x plus r1 of x, and that is equal to g of x times q2 of x plus r2 of x, and that implies g of x times q1 of x minus q2 of x is equal to r1 of x minus r2 of x. Now there are two conditions. Case 1, r1 of x minus r2 of x is equal to 0, and that implies r1 of x equal to r2 of x, and because this is 0, q1 of x minus q2 of x equal to 0, and that implies r1 of x equal to r2 of x and q1 of x equal to q2 of x. Now case 2. Case 2 meaning r1 of x minus r2 of x is different from 0. This is not possible, but we are just assuming that this is not equal to 0. And that implies, see, if this is not 0 and this is a polynomial and multiplied by this, the whole polynomial will be of degree greater than or equal to the degree of polynomial of g of x, which is not true because r1 minus r2 is a polynomial of degree less than g of x, and this implies that q1 of x minus q2 of x should be 0. This is actually not possible. If it is possible, this is true, and which implies q1 of x equal to q2 of x, and which implies r1 of x is equal to r2 of x. Because if this is equal to q1 is equal to q2, then this will become 0. The whole left hand side will become 0. So this is 0. So in either way, q1 and q1 is equal to q2 and r1 is equal to r2, and that shows the uniqueness of q and r. So q of x and r of x are unique. So another corollary of this division algorithm f of x belongs to f of x and a belongs to f, then x minus a or x minus a is a factor of f of x if and only if a is a 0 of f of x. See, you have to remember that the 0 of f of x does not need to be in f. It may be in an extension of f. But if it is in f, then this is a factor of f of x. And if it is a 0, if a is a 0 and a belongs to f, then x minus a is a factor. This looks very simple, but remember a is in f. Then only this will be a factor, otherwise it won't be a factor. For example, if you take f of x is equal to x square minus 2 and our f is q, then this cannot be factorized in q of x. See, x minus root 2, x plus root 2, these are the factors of this, but this does not belong to q of x. Okay? So, if this is an element of f, then this is a factor. Okay? Otherwise it is not. So, there are two parts here. Let a belongs to f be a 0 of f of x, and that implies f of a is equal to 0. Now, f of x is equal to x minus a, this is our g of x in our division algorithm, times q of x plus r of x, where the degree of r of x is strictly less than the degree of x minus a, and that is equal to 1. So the r of x, the degree of r of x has to be 0, meaning r of x is a constant, and that implies r of x is a constant polynomial, and that implies f of x plus x minus is equal to x minus a times q of x plus c, where c belongs to f. Now we will apply this rule. F of a is equal to, this is actually 0 times q of x plus c, and that implies this is actually 0, c equal to 0, implies f of x is equal to x minus a times q of x plus 0, which is actually this, same as this. So that implies x minus a is a factor of f of x. Now let x minus a is a factor of f of x, and that implies f of x is equal to x minus a times g of x or q of x for some q of x in f of x. So that implies f of a is equal to, this is actually 0 times q of x, and that is equal to 0, and that implies a is a 0 of f of x. We'll do another corollary of this division algorithm. Let f of x be a non-zero polynomial of degree n. Then f of x can have at most n values and zeros in f of x, sorry, in f. Again, remember that the zeros of f of x does not need to be in f. Okay. Now, if there are no zeros in f, then we are done. We have to show that at most n zeros in f. So, if there are no zeros, if there are no zeros of f of x are in f, then we are done. So let us assume that a belongs to f, a1 belongs to f, and a1 is a 0 of f of x. Implies f of x can be written as x minus a1 q1 of x, where the degree of q1 of x is n minus 1. So continue this process until we get f of x equal to x minus a1, x minus a2, that is x minus ar times qr of x, where qr of x does not have a 0 in f. So this implies that r is strictly less than or equal to n, because it cannot go beyond n. It can have only up to n factors. Now the question is that if we express like this, can we have another b which is different from any of this that could be a 0 of this? So let b is different from, b belongs to f, and b is different from ai for all I belongs to 1 comma r. And so yeah, let us assume b is like this. So what is b of f of b? F of b is equal to B minus A1, B minus A2, B minus AR, QR of B. So, because F is a field, that means no zero devices, B minus AI cannot be 0. Because FB is not equal to 0, BI cannot be equal to 0 because BI are different from AI. And FB cannot be 0. F is a field, so there is no zero devices. So none of these are zeros, and therefore the product is also not equal to 0. And QR of B is different from 0 because QR of X does not have a 0 in F. That is how we are factorizing this, because QR of X does not have a 0 in F. Okay, and that implies F can have at most n zeros in F. We will do one more corollary of this division algorithm. Let G be a finite subgroup of F star comma dot, where F is a field. Then G is cyclic. See, F is a field means there are two operations defined here, binary operations defined here, addition and multiplication. And this is actually a multiplication. So we are looking at a group of non-zero elements from F with multiplication. And G is a finite subgroup of this. So if F is a finite field, definitely G is going to be a finite subgroup. Okay? See, all we need is G should be finite. So G is a finite subgroup of F star multiplication proof. Implies G is finitely generated abelian group. It is finitely generated because it is finite. Abelian is because it is coming out of the field F. So, using the fundamental theorem on finitely generated abelian groups, G is isomorphic to Z D1 dash dash D C D N for some n in C. And each ZDI are cyclic. Now what we will do is let M be the least common multiple of d1 dash dn, and that implies m is less than or equal to d1 dn. Okay, now let alpha belongs to G, and that implies alpha to the power of m is equal to 1, because this is a multiple of d1, d2, etc. dn, and that implies alpha is a 0 of x to the power of m minus 1 in g of x. Okay, you don't need to write it in g of x, it's in f of x, because it's not in g of x, it's f of x. That implies x to the power of m minus 1 has at most m zeros in G. And G contains d1 times d2 dash dash dn elements, because G is isomorphic to this, and that implies m is greater than or equal to d1 data times dn, and that implies m is equal to d1 times data dn, and that implies the primes appearing in each of di's are different. And that implies z di d1 times z d2 times dash dash z dn is isomorphic to zm, which is cyclic, and that implies G is